For NEC2, very powerful simulator for antenna design, modeling, and optimization. 2D, 3D geometries can be generated. We want to map it with Smith chart. We want to check impedance, SWR. What about the reflection? How much reflection is there? As all of you are from electronics domain, this is very important point. How much signals are radiated back? Okay, and if most of these are radiated back, then we have to go for its analytics, okay, or optimization. Just a minute. So this is the website qsl.net, and for NEC2, easy, free and open source, freely available on this. Some geometries that can also be done. Okay, you can download it. So I'm showing you very quick screenshots. So these type of analytics we can do. So for example, impedance analysis, we want to work with geometry. Okay, NEC editor is available. I will cover that part also. Okay, in this way, far field pattern. Now we will see how to work with. I'm opening the laptop. This is for NEC2. I have already installed in my laptop. Okay, this one. Now, which type of antenna we want to simulate? So I'm closing any previous file. For example, so this one is the simulator. I will show you very simple demonstrations on dipole antenna, Yagi Uda antenna, even microstrip patch antenna we can work. But we will see that microstrip patch antenna is not suitable for implementation in this platform. If we want to simulate microstrip patch antenna, then we should go for open EMS. Okay, open EMS. I will cover that part also very quickly. Open EMS. This is, if you want to work with underwater antenna simulation, submarine antenna simulation, underwater acoustic network, because many times researchers work on underwater acoustic or radio network. In that case, microstrip patch and in that case for NEC2 will not be suitable. Okay, certain modifications we have to perform in that. For underwater, for microstrip patch antenna, we work with open EMS. This one is multi-dimensional. Yes, it is in Windows, for Windows, Mac both. Because my system is Windows based. I will show you in that. Okay, this one. So again, I'm repeating this part. So in very simple language, we will see. If I want to create antenna, wire-based antenna, for wire-based antenna, we work with for NEC2 in very simple layman analogy. Okay, for wire based, whether it is whip antenna, bipolar, dipolar, wire antenna within sea, within ocean, wire antenna underwater, for NEC2 is fine. But microstrip patch antenna, in that case, open EMS. Very simple. Okay, for NEC2. Now we will see some simulations. Okay, I'm opening for NEC2. This is for NEC2, and I will explain how to work with this software. So first of all, I will show you some implementations. If I want to create a beam antenna of 100 megahertz, FM antenna, half wave dipole antenna. So these implementations I will show you. First of all, I am showing you the source code. Okay, we will understand by which way code is written. Very simple. Okay, so this is the script. Half wave dipole antenna in for NEC2, and after that we want to see its spectrum, we want to see its uh, Smith chart readings and other details. So CM for comments, very simple. CM for comments. In comment you can write anything. So I have written this one. This is dipole antenna of 100 megahertz. Dipole antenna of 100 megahertz means this is FM station, for FM station, because 100 megahertz is generally for FM radio station. Okay, just for very simple example. Now I want to create an antenna to catch this frequency 100 megahertz with half wave dipole antenna. So this is my message. I can write anything. I can write my name also. This is CE. CE stands for comment end. It means comment is complete here. Now here actually work is going on. GW. GW means G. This is wire. Dipole antenna means one antenna divided in two parts. Is it correct? Because all of you are from core electronics domain. Antenna in center we have some connector. Okay, so what we are doing, we have one antenna of length. How much length? Now mathematics will start. Physics will start. I want to catch 100 megahertz signal. To catch 100 megahertz signal, how much length of antenna I need? That 300 divided by that particular aspect. Okay, so this one minus 0.75 to 0.75, it means 1.5. 1.5 means 1.5 meter antenna. If I want to create 1 meter antenna, in that case I will write here minus 0.5, this one 0.5, but I will have to change this frequency. Is it correct or not? We have to we have to map frequency with antenna. Okay, so if I want to catch 100 megahertz, so 100 megahertz means hundreds multiplied by number of zeros. We divide that value from light speed. Okay, what will be the output? 3. 3 divided by 2, dipole antenna 1.5. 1.5 in two parts. Why two parts? Because we have to put in this format. Okay, now this, what is this 21? This wire, this particular one, this one is wire number. This is one wire, one particular antenna wire or any particular substance. We have divided it in 21 parts. We have divided complete wire in 21 parts. Why 21 parts? You can take 11 parts also, you can take 31 parts also, but number should be odd. Generally we take odd number. Why odd number? Because if we are dividing with odd number, then exactly at center we will be able to put a particular connector. Okay, if we are dividing by 10, if we are dividing by even number, in that case where will be center? Okay, identification of center will be difficult. But if we are dividing with odd number, in that case, so what we are doing, 1.5 1.5 meter wire we are dividing in 21 parts, and at 11th part we are connecting, and we are giving a particular voltage. Where is the voltage? Ex is the voltage that you relate with excitation. Ex is your excitation. Okay, now at wire number 1 we are giving 1 volt. Okay, 1 volt we are giving, and this particular 0, actually this specific is having a particular format. Major part is simulation. I am opening this file, dipole antenna, this one, and this one high half wave dipole, or we can take this FM antenna also. Okay, this FM antenna we are taking. Now you can see this one, radiation pattern. Okay, now with this radiation pattern we want to see some details. Loads, what is SWR? 1.82, is it acceptable or not? Okay, it is acceptable to some point, but 2 is not acceptable, 3 is not acceptable, up to 1.5, 1.67 it is fine. Okay, but we can optimize it. Okay, this one voltage, this one impedance. Now show, we want to see Smith chart. This is the Smith chart. In Smith chart we can see on 100 megahertz what is frequency, what is S11. S11 is 0.29 at 65.1, and impedance is 81.8. Generally we map or we connect impedance with 50 ohm. Is it correct? Okay, we create a benchmark, we work with benchmark of 50 ohm, but here it is this one 81.8 ohm. 81.8 plus J47. So you can see that without creating any Smith chart manually, we will be able to work with it. In same way, for example, we have one more script, half wave dipole antenna. Okay, this one. Now we can check it. Now if we want to create a Yagi Uda antenna, that can also be done, because that is also wire based, that is also connector based. Okay, so if we want, now if we want to work with underwater antenna, for example, for research work or for publication work, because many times we struggle for good publications, so this is also a very good area of research, underwater antenna. You might be knowing that when we work with underwater or sea or acoustic, in that case, antenna size is reduced by 9, by 1 by 9. Okay. For example, on ground, my antenna size is 20 meter. In sea, 20 by 9. Only that will work. And if we want to work with long waves, in to map with long waves, we need long antenna. But we have divided by 9. So how to map, how to synchronize with that value, so that even after dividing by 9 we will be able to capture those signals. Are you getting this point? Okay. Now we will see why microstrip patch antenna fail. Okay, so again I'm showing, for example, one simulation I have created related to 100 megahertz. Here this one is beam antenna, and beam yeah, two element beam Yagi for 100 megahertz. Okay, this one. So this code I will share to all of you at end of this session, so that you will be able to work with it. Very simple. It might be looking difficult, but very simple, 4 to 5 lines of code. And nowadays AI is available. Okay, with AI we can modify. For example, some new concept is in my mind, so we can take help of AI, chat gpt, Gemini, perplexity, and after analyzing parameters we can change these values. Okay, now this particular antenna we want to simulate for 100 megahertz, again for FM station. Okay, so this one, and other so many details available here. So this is 3D viewer. If you want to view it in 3D, So I'm again executing it with some more details. Okay, in this particular radiation pattern can be modified also in simulation. This is for NEC. I'm opening again. So by default it is working in this way. Now calculate this one, use original file, generate. This one. Okay, if you want to view it, any details, any interior details we will be able to see. So you can see what is the what about impedance value. So loads, so SWR so much high. Okay, now I want to see simulation of patch antenna. Okay, so one script related to patch antenna we will see, and whether it is successful or not, and why not successful. So this is microstrip patch antenna, and here you can see this one, NEC output, generate. Okay, so now we will see its load. So SWR stars, it means not valid. Okay, no valid output is available. If I want to see its Smith chart, so impedance minus 0 minus j, so it means it is not able to analyze, it is not able to give effective results in this platform. So if we want to work with microstrip patch antenna or some high dimensional antenna, in that case we go for open EMS. Okay, so for classical antenna it is fine. For general purpose like a wire based antenna, if you want to work, you will be able to work with it. Okay, so one file I am opening here. After that I will show you how to simulate microstrip patch antenna in open EMS. Very quickly we will see that part also. So calculate. After that this one, geometry, and its impedance value, voltage, different other parameters. Now this output can also be linked with GNU radio. That is also possible. Okay, what I want to do, for example, uh, I want to use these results, these radiation patterns. I want to save in a file, and those files I want to use in SDR. So this is antenna simulation. But antenna radiations or these parameters I want to visualize in form of spectrum. That is also possible. So spectrum generation, as we have seen in FM radio, in international FM radio. So if same type of spectrum I want to view, so in that case we go for GNU radio.